Okay, wonderful good afternoon, ladies and gentlemen. It's lovely to be here today, and I hope that things go well. Okay, wonderful good afternoon, ladies and gentlemen. It's lovely to be here today. Okay, so this was a little bit of a sound check. So if you can hear me and if you can see me, can you please give me a thumbs up or write any comments or something like that, so that I know things work and you can see me and hear me. Thumbs up, or send me a like or a heart or a kiss or something like that. That would be really nice. We have got a few people joining. So, can you hear me? Okay, good. Oh, okay, we've got a couple of people coming in. That's great. Oh, Hattie is here. Amy Louise is online, so that's great. Hello. Hope you're doing all right. So, can you hear me? Can you send me a thumbs up, please? If you can hear me, that is. Does the sound work? Yay, thumbs up. Yeah, that's great. Thank you. So, and is the sound quality okay? Okay, I get thumbs up. Now that's excellent. So it looks like this is working. I'm very pleased. I've tried it only once, and obviously it wasn't perfect. Now this is not going to be perfect, but hey, let's see if this is sort of the lecture of the future. So wherever you can get Facebook, you can perhaps get a lecture. So what I want to do with you today is really give you a refresher of what you have done in the first year, when we, for example, discussed how to make up solutions, how to calculate how much you have to weigh in for a solution and things like that. And I really want to use dimensional analysis, because that is really an easy way of dealing with these things. Why is it so important? Well, it is important because this is what you do every single day when you work in a lab. You make up solutions, you prepare these solutions, and this is really the bread and butter for all biochemists. So let's go to a typical question. So just quickly, a thumbs up, then if you can see this properly. Can you see that? Thumbs up? Yep, yep. Excellent, good. So that works very well. So in this one, in this question here, as I said, it's a really typical question. You need to make up 100 milliliter of a 0.1 molar solution and the substance has a molecular weight, has a molecular mass, I should say, of 269 gram per mole. And how much do you really have to weigh in? Now, of course, you can try and figure that out. I would suggest that I show you in the first place how you can easily do that. So in dimensional analysis, what we do is we use the units to guide us through the calculation. Guide through calculation. Calculation. So here we've got unit of milliliter, obviously. This one here is a little bit more tricky. Obviously this stands for mole per liter, so molar. And here we have the unit gram per mole. And in the dimensional analysis, we basically write down the unit we are looking for. So here we ask, how much do you have to weigh in? And obviously this unit would be in grams. So we are looking for the grams. And the next step obviously is that we are looking for a unit in our givens here, in this part here, that has gram in it. And very clearly, as you can see, this is this one here. So we write this as 269 gram per mole. Now what we have, obviously, is we have our right unit. We want grams, we have grams here. The only thing that is a bit of a nuisance is this guy here, is this mole. So we need to find something with which we can multiply this term so that the mole cancels out. And do we have any moles in our givens? Yes, we have a mole here. So we just simply write it as 0.1 mole per liter. Okay? Now what we can do is we can cancel out the mole. That's gone. So we still have our gram here, this one here, but now we have the complexity of having a liter down here. Now obviously we need to cancel this liter out. Do we have liter up in our givens here? Yes, we have got this one here. And we can write this as 100 times 10 to the minus 3. That's the milli here. Milli is 10 to the minus 3 liter. And what we've got now is our liter cancels out. So what's the unit that we have left? We have a gram here. The mole has cancelled out. The liter has cancelled out. So our final unit is this gram here that we have. So we can write now 269 gram times 0.1 times 100 times 10 to the minus 3. And we just simply put that into a calculator. What do you get when you put that in the calculator? Please put something in the comment section, please. So comments, what do you get? Yeah. Amy Louise says 2.69 gram. Do we trust Amy Louise? If we trust Amy Louise, give her a thumbs up. Yeah, nice one. Good. So we have 2.69 gram that we have to weigh in. So that was pretty straightforward. Now let's have a look at another question. So I just remove this. So here's another question. And I want you to try this out yourself, and then we will go through it. Yeah, Rachel got the 269 grams, 2.69 grams as well. Okay, excellent, fantastic. So again, we have a weighing in question. So what is the unit that we are looking for? Comments, please. Anyone? Need to improve my speed on the calculator. Yes, I know this is an issue that Emilio is talking about, because at the end of the day, you really need to know what you're doing in the lab, and you need to have your calculator there. So yes, Dylan, you're right. We have grams that we are looking for. So do we have any grams here? Yes, we have. Where is the grams? Obviously, I hold my pen here. So we have 660 gram per mole. Now, the grams is good. That's what we want. But the moles, we don't want that. So we have to multiply it with moles. And we have here the unit millimole per liter. That's the capital M is mole per liter. So we have 125 times 10 to the minus 3 mole per liter. Now we see that the moles cancel out. We still have the grams here. Now we need to get rid of the liter. Do we have any liters anywhere? Yes, the liters are in here. So we have times 10 times 10 to the minus 3 liter. And again, the liters cancel out. And what we have here is 660 gram times 125 times 10 to the minus 3 times 10 times 10 to the minus 3. And obviously gram is the only unit that's left. So anyone who wants to do the honors to do the calculation, put it in your comment section and you get a few likes and maybe even a heart. Anyone? What do we get? Emilio says 0.825. Dylan says 825 grams. Could it be that there is a 10 to the minus 3 missing? So who is right, Dylan or Emilio? Okay. So there is a 10 to the minus 3 missing. And Dylan said that he probably agrees with Emilio. So this would be 0.825 grams. Excellent. So I think you probably got the hang of it. Do you want me to do another example? Send me thumbs up, or oh yeah, let's do this example here. Because there's something new in it. Okay, so in this one here, we have, again, milliliter, that's a volume. We have a concentration, 1 millimolar, that's a concentration. So here we have, again, mole per liter. Here we have, again, milliliter, but we don't really have a molecular mass. The molecular mass, usually proteins are given with kilodalton. So you need to really understand what kilodalton means. And kilodalton, we can write this also as 66,000, that's the kilo, and this Dalton actually stands sort of for gram per mole. So in a way, this kilodalton, which is usually used for proteins, is nothing else but a little bit decoded gram per mole. And now we can, again, we can do that very easily. So again, we are looking for the grams. Do we have grams? Yes, we have the grams. We have the 66,000 gram per mole. Now the gram is okay. And all we need to do is get rid of these moles here. So we need to multiply it so that we get rid of the mole, and we've got mole here in this part here. So we can write this as 1 times 10 to the minus 3 mole per liter. Now we see that the mole cancels out. Now we still have the gram here, but the liter is a little bit of a nuisance. So let's cancel that out, and we have liter here. We have 10 times 10 to the minus 3 liter. The minus 3, that reflects the milli here. Likewise here, milli and 10 to the minus 3. And what we see is that the liter cancel out. And the only unit that we have got left is gram here. So that's good. So we have 66,000 gram times 1 times 10 to the minus 3 times 10 times 10 to the minus 3. Okay, and on your calculators, please. Let's see what this gives us. And if we get the right number here. Okay, so what do we get? How much do we need to weigh in? Amy Louise is putting 0.66 gram, excuse me, with a question mark. No, don't put the question mark in, be confident. Emilio says also 0.66 gram, and yep, you got it. Hey, great, I love that. So we get 0.66 gram. Excellent, guys. If you got that, then we are in business, and you can be fairly confident that you actually got the right method. Fantastic. So let's have a look at another question that I've prepared for you. Oh, here is a very common question again that is something that quite frequently crops up. We need to make up a 10 milliliter solution of a 1% weight per volume. How much do we have to weigh in? Now we need to remind ourselves, what does 1% actually stand for? So what does that mean? Can somebody put that in the comment section? What does it mean? What does 1% actually mean? Can you remember that? 1%? One per 100. Rachel is absolutely right. And Amy Louise, yes. Amy Louise says it is 1 gram per 100 milliliter. And you are absolutely right. And here this weight stands for gram and the volume per 100 milliliter. So it's 1 gram per 100 milliliter. Absolutely correct. So we want to make 10 milliliter of 1 gram per 100 milliliter. So how much do we need to have? How much do we need to weigh in? Well, again, it's fairly simple. If we had 100 milliliter, then we would need 1 gram, right? Because that is what it says. But we only have 10 milliliter. So this is 1/10 of our gram, and therefore it would be 0.1 gram. So we would need to weigh in 0.1 gram. Does it make sense? If it makes sense, give me a thumbs up, please. Yay, I got some. Yes, I got some thumbs up. Great. So you think you can do that yourself? That would be absolutely smashing. Let's have a look at another typical example. Aha. Here. You want to try that out yourself? What does this actually mean? Again, we have 0.01 gram per 100 milliliter. And this time we want to make 1 liter of it. Okay? So we have 0.01 gram in 100 milliliter. In 1 liter, how much would we have? Yes, Rachel, absolutely spot on, 0.1. And Dylan says we have eventually 0.1 gram in 1 liter. And you are, Dylan and Amy Louise say 0.1 gram, and you are absolutely right. All we need to do in order to get from 100 milliliter to 1 liter, you have to take it this one times 10, and this gives us 0.1 gram. Excellent. Well done. Oh yes. Good, Rachel, because you said 0.1, and I was just about to say what? Bananas or whatever, and you put in grams. So these units are really, really important. So well done that you corrected what you just said. Okay, here's another type of question. Not type of question, but something that you might encounter in the lab, and again that is very, very frequent, that you're working with a stock solution. So here the important thing is that you have a stock solution and that you want to have a working solution. So how do you deal with that? Well, you can use the C1 V1 equals C2 V2 equation here, which you have probably seen quite a lot of times. So what does this actually mean? Where does it come from? So here we have our stock solution. And here we have our working solution. And here we basically want to have 50 milliliter of this 1 millimolar solution. Now what we want to have basically here is a certain amount of moles. Okay? And where does this certain amount of moles come from? Well, this certain amount of mole come from our stock solution. So how many moles do we have actually in here? We can very easily calculate that. We can say how many moles do we have? We have 1 millimole per liter. So we can say here we have 1 times 10 to the minus 3 mole per liter. So we want the moles, that's okay. The liter is a little bit of a nuisance, so we multiply that by 50 times 10 to the minus 3 liter. So that would be our amount of moles that we have here. Now we need to take the same amount of moles from this one here, and basically this is this equation here, C1V1 equals C2V2. So we are basically looking for V1 equals C2 V2 divided by C1. And here that would be our 50 milliliter, sorry, that's V2, times 1 millimolar divided by the stock solution, which is 10 millimolar. And we see millimolar cancels out, and all we have is 50 milliliter divided by 10, so that gives us 5 milliliter. We would need 5 milliliter of the stock solution. So how would you make up this buffer? Well, you would make up 5 milliliter stock. And how much of water and buffer would you need? How much water and buffer? Oh, good point. Why haven't I converted into moles? Well, I could convert that into mole, but I don't have a volume here in the stock solution. So it's a little bit, or do you mean about millimoles? Do you mean the millimoles that I haven't converted? Okay. Actually, because actually I have both the units are in millimolar and millimolar, so I don't really have to convert that into moles. As long as I've got the same units, I can use them here in this equation. And I just asked how much of the water, and Rachel said 45 milliliter. You are absolutely right, Rachel. Well done. I think people should send you a heart, because we have 5 milliliter of the stock solution. We want 50 milliliter. So therefore we need 45 milliliter of water or buffer in order to get a total of 50 milliliter. Now I have a slightly different approach to something like that, and that quickly let me show you how I use this approach. Whenever I work with stock and working solutions, I think of a guy who goes into a pharmacy and he just got a prescription from a doctor, and the doctor says, give that guy 50 milliliter of 1 millimolar. Oops, I got this wrong, the wrong way round. One millimolar solution. So that's in the pharmacy, and he stands opposite a really hot pharmacist. So that's the desk here, and here's the pharmacist. And the pharmacist says, I'm so sorry, we don't have this solution, we only have 10 millimolar. So what you see here is exactly the equation, 50 milliliter times 1 millimolar. So it is 50 milliliter times 1 millimolar divided by 10 millimolar. So it is basically here, doctor says times doctor says, here the millimolar and here the milliliter, and this is what the sexy pharmacist says. So it's basically doctor divided by pharmacist. Okay? It's just for me to remember that. In our pharmacy where I grew up, we had a really hot assistant, and therefore I will never forget this equation, how to basically deal with stock and working solutions. But I don't want to be quoted on that. So last one, let's see. I know that a few people had to leave. Again, this is a very, very common thing and exactly along the line of what we just discussed. So you have a stock solution of 100 milligram per milliliter. You want 500 milliliter of 100 microgram per milliliter. So how do you do that? Well, again, very simple. The doctor says we need 500 milliliter of 100 microgram per milliliter. And the hot and sexy pharmacist says, sorry, we have only 100 milligram per milliliter. Now here the slight difference is that we have it here in milligram and here in microgram. So what we need to do is really bring it to the same basically unit. So we can write here 500 milliliter times, we can convert microgram into milligram, so that would be 0.1 milligram per milliliter divided by 100 milligram per milliliter. Okay, so what volume do we need? We would therefore need, anyone? Can anyone calculate that, please? We see that the milligrams and milliliters cancel out, so we've got 500 milliliter times 0.1 divided by 100, and that gives us Amy Louise says 0.5 milligram. Be careful, the milligram cancel out. Yes, you are absolutely right. We would get 500 milliliter. We would get 0.5 milliliter, which is the same as 500 microliter. Now, this is, yes, Emilia, absolutely right, 500 microliter or 0.5 milliliter. Now, what people very often do is they make up the stock solution. This stock solution, if you look at it, this stock solution and this working solution differ by a factor of 1,000. And that is deliberate. Because what you need to do is, if you have a factor of 1,000, all you need to do is use the volume and divide this by 1,000. So 500 milliliter divided by 1,000 equals 0.5 milliliter or 500 microliter. So you divide it by 1,000, and all you need to do is really take this number here and divide the milli by 1,000, which gives you micro. So if you have, for example, let's say you have a 60 milligram per milliliter solution, and you want 25 milliliter of a 60 microgram per milliliter solution, all you need to do is you take 25, now this is 1 in 1,000 again here, 1 in 1,000, you take 25, and this time not milliliter but microliter. So you just simply take that and divide the milli by 1,000. And that is a very common trick when you, for example, use antibiotics. So antibiotics, very often you make them as 1,000 times stock solution, 1,000 times stock, and then you just simply don't really have to think a lot. You just simply take the volume that you want and go down one of the potencies, so from milliliter to microliter, and you have it sorted. So I think these are all the problems that I can think of at the moment that you can encounter in the lab to making up solutions. Do you have any further questions now? Any further questions? In this case, if there are no further questions, I hope this whole thing made sense. And if you've got any problems, just let me know and I will try to sort you out. So thank you very much for watching. What I will do is I will try to upload this onto the BI600 page, but it should also stay here on Facebook. And well, good luck with your lab-based projects and have fun. I'm going to do a little bit more sessions then in the future on data analysis. So if you've got any questions, post them here on Facebook or email me and I will try to address them in another live session. Thank you very much and enjoy.